Am I audible? Okay, okay. Sorry guys. So this is quick brief about me. I am Satya with all these credentials. This GATE AIMER'S series started on 14th November, where we are discussing all important subjects, important concepts. So attend these classes regularly and get the most benefit out of it. Rakesh Talreja sir will be taking a mega workshop on 18th December at 12:30 p.m. where sir will be giving you 7 key career prospects through GATE exam. So attend this class live, and 2024 aspirants, please gain this career prospects from our expert Rakesh Talreja sir. And for electrical, electronics and instrumentation students, the good news is that we are going to discuss live the last 5 years PYQs solutions. So from 18th December, so attend these classes regularly. And our mega mock challenge, which is active till 20th December 2023 aspirants, take this mega mock challenge where you will get all India level ranking and you will get the feel of writing the GATE exam using virtual calculator. So it would be useful for analyzing your performance at a better way, right? Lalit Yadav, voice is very low. Can you please check now? Lalit Yadav and everybody, now am I visible and audible clearly? Same. Okay. Lalit, I think it is the issue from your side. Could you please refresh? Okay guys, let us get into the session. Binary heap. What is binary heap? A binary heap is a binary tree. So it's a type of binary tree. So the maximum number of children are 2 because it is binary tree. It can have 0 children or 1 child or 2 children, any node. And it is a binary tree with 2 conditions satisfied. What are the 2 conditions? First condition is it should be a complete binary tree. Yesterday we have discussed what is complete binary tree. It should be filled from top to bottom, left to right, except the last level. All the other levels must be completely filled. So this is what we call as structuring property, or even you can call it as shape property. Shape property. So a binary heap must be complete binary tree. And what is the other condition? Parent must be either greater than all its children or less than all its children. The parent value must be greater than all its children or less than all its children. This condition also must be satisfied. This is what we call as ordering property or heap property. Heap property. So for any binary heap, these 2 conditions must be satisfied. When parent value is greater than all its children values, then that is said to be max heap When parent value is less than all its children values, then we call it as min heap. Example is here. If you look at the left side diagram, 1 is less than 3, 2. 3 is less than 4, 6. 2 is less than 5. Right? So, every parent is less than its children. Hence, it is min heap. And you look at the right one. 6 is greater than its children 5 and 3. 6 is less than its children 5 and 3. 6 is greater than its children 5 and 3. 5 is greater than its children 4 and 2. 3 is greater than its child 1. So, every node, every parent is greater than its child. So, it is max heap. Right? Into the binary heap, if you want to construct a binary heap, what you have to do? You have to insert an element one by one. So, how do we insert any element? We will insert the elements in the level order, left to right. Why? To satisfy complete binary tree property. Once you insert, that value may not satisfy the heap property. So, you have to heapify. Means, if it is a max heap, we will check the inserted value with its parent value. If the parent is smaller, we will swap. So, we do this recursively until heapify property, this ordering property satisfy. Okay? And how we delete from binary heap? We don't directly delete from binary heap. You can't delete any element that you want because it violates complete binary tree property. You can't delete some middle element or any internal node. Leaf nodes only can be directly deleted. That too, last leaf node, if you delete, the complete binary tree property still preserved. So, to preserve CBT property, what we do? We will swap the root element with last leaf node. We will swap the root element with the last leaf node, then delete it. So, always deletion happens where in the binary heap? By default at root node. But whenever you place leaf node at the root level, again it is against to ordering property. It may not be max heap, may not be min heap. So, what you have to do? Heapify. After deletion, heapify, so that heap property satisfy. Okay? So, let us understand this insertion and deletion with example. Suppose we are given this max heap and you want to insert 81 and 68 in the same order. So, first construct a max heap. 75. How we construct? In the CBT order. That means you start filling from top to bottom, left to right. 62, 43, 3030, 5757, 6060. Check, is it a max heap? Yes. 75 is greater than its parent, 54 greater than its child, 54 is greater than its child, 62 is greater. So, it is max heap. Now, insert 81. Where you insert? to preserve CBT property, where we insert as left child to 43. As left child to 43. Now you check whether it is satisfying the ordering property or not. It is not satisfying the ordering property. So what we have to do? Heapify means swap 43 and 81. So 81 will be here, 43 will be here. Check 81 with its parent. It is smaller. So swap 81 and 54. Recursively apply this till root. 81 is compared with 75. 75 is the smaller. So swap. So 81 comes here, 75 comes here. So after first insertion, this is what the binary heap. Now let us do second insertion. What? 68. Where we insert 68? As right child to 54. Now compare with its parent after insertion. 68 is greater than 54. So what you have to do? Swap. 54 comes here, 63 comes here. Compare this with its parent. 63 is smaller than its parent. So yes, no need to swap. So after two elements insertion, the resultant binary heap is 81, 75, 62, 63, 3030, 5757, 60, 43 and 54. So insertion is clear for everyone. So with this, insertion must be clear, right? Now let us see how we can do deletion. Suppose we are given these elements and we wanted to delete. So first construct a max heap. 75, 54, 62, 43, 30, 57, 60. Now I want to delete. How I can delete? I can't directly delete. Deletion always happens at the root node. So 75 is first swapped with 6060. Now 75 became the last leaf. Now you can delete. But now it is neither max heap nor min heap. So you have to make this max heap. So how I can make? Compare 60 with max of its child. So max of 54 and 62, 62. So swap with it. 62 comes here, 60 comes here. Compare 60 with its child, 57. Yes, it is bigger. So after first deletion, the tree is 62, 54, 60, 43, 30, 57, that's it. This is the binary heap after first deletion, right? Now let us do second deletion. I want to do second deletion. How I can delete? 62 swapped with 57. So 57 comes here, 62 comes here. Now delete 62. Now heap 5. 57 compared with 60. 57 is small. So swap 57 and 60. That's it. So after second deletion, the resultant binary heap is 60, 54, 57, 43 and 30. Clear? So with this, how deletion happens from heap also must be clear, right? And from heap, guys, this is what we can expect in the GATE one possible model question, that is total number of orderings possible. How many orderings are possible means how many binary heaps we can construct. Whether it is a max heap or mini heap, no problem. So how many we can construct? For that, we use the DP approach, dynamic programming approach, because it has the properties overlapping of subproblems and optimal substructure property. So applying this DP approach, we can solve this, and the recurrence relation for this you can use as this one. If there are more than 2 nodes, you can say, not even 1 node, or for more than 1 node also it works. What? If there are n elements, n minus 1 C L. L means number of nodes in the left subtree. Number of nodes in the left subtree. And recursively you do for left subtree and right subtree. And when n is equal to 1, means only one node is there, that is 1 only. That is 1 only. Right? Let us understand one example. How many orderings are possible? How many binary heaps are possible with 5 elements? Suppose this is the question we got. With 5 elements, how many binary heaps possible? Before I apply the recurrence relation, you tell me, in these 5 elements, if I construct the heap, this is how the heap would be, because it should be complete binary tree. This is how I can construct. So on the left subtree, I have 3 elements. On the right subtree, 1 element, 1 will be the root. So among 5 nodes, 1 gone for the root. So 5 minus 1. We have more 4 elements. In these 4 elements, 3 elements I have to choose for the left subtree. Multiplied by. Apply the same for left subtree. In the left subtree, 1 is gone for the root, means parent. And in its left subtree, how many nodes are there? So remaining are how many? 3 minus 1. 2. C. In the left subtree, only 1 node. Multiplied by. Its right subtree is having only 1 node. So it is 1. This is T of R. This is T of R. that is again one node. So it is 4C3 multiplied by 2C1 multiplied by 1 into 1. So what is 4C3? If you know direct formula, you can write, or else you know how to calculate. It is 4 into 3 factorial divided by 1 factorial into 3 factorial. And 2C1 is 2, or if you don't know that, you can write 2 into 1 factorial by 1 into 1 multiplied by 1 multiplied by 1. So this is 4 into 2 into 1 into 1, that is 8 binary heaps are possible total. So total how many binary heaps we can construct? With 5 elements, 8 binary heaps we can construct. Okay? As this is the most expected model question nowadays, let me take one more example. Okay? If there are let's say 11 elements, how many binary heaps are possible? If n is equal to 11, number of binary heaps possible. First, with 11 elements, construct a complete binary tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is how we construct CBT, level wise, top to bottom, left to right. Now, in the 11 elements, one element is definitely root. So we have more 10 elements. In that 10 elements, I have to choose how many elements for the left subtree? 7 elements in the left subtree. So out of that 10, I have to choose 7 multiplied by, this is the left subtree. So recursively you apply the same. Now you take this as a tree. We are having total 7 nodes. In that, 1 gone for the parent. So root, subtree root. So I have more 6. In that 6, I have to choose any 3 for the left subtree. So 6C3. Recursively you apply. So this is its left, this is its right. So in this left subtree, 3 nodes are there. In that, 1 gone for the root. So in the 2, I have to choose 1 for the left subtree. Now its right subtree is having only 1 node. So it is 1. Then its right subtree is having 3 nodes. So again, in that 3, 1 we have to choose for parent. So again I am having this. Now complete left subtree is over. Now right subtree. So this is the right subtree. In these 3 nodes are there. In these 3, 1 will go for the parent. So I have more 2. In that 2, 1 I have to choose for left. So I can choose in 2C 1 ways. And right I have only 1 node. When there is only 1 node, it can be chosen in 1 way only. So the total is 10C7. 10 into 9 into 8 into 7 factorial divided by 10 minus 7 3 factorial into 7 factorial multiplied by 6C3 6 into 5 into 4 into 3 factorial divided by 3 factorial into 3 factorial multiplied by 2C1 is 2, 2C1 is 2, 2C1 is 2 and all are 1. So, I can just ignore them. So, now 3 factorial is 6, 7 factorial gone, 3 factorial is 6. So, 6 goes in 72 12 ways, right? So, I have finally 10 into 12 into 5 into 4 into 2 into 2 into 2. You can use calculator. So, let me use calculator, all dear friends. It is 10 into 12 into 5 into 4 into 2 into 2 into 2. 19,200 ways. How many ways? 19,200 possibilities. Understood, everyone? So, this is one most expected question from the binary heap. So, in this way, you please practice. Okay? Now, let us move on to the practice part. Before that, our BYJU'S Exam Prep is offering GATE and ESE test series, where you can get unlimited access to full-length mock tests and subject-wise tests. The link will be given in the description box. So, go to that and register for our acquire our test series. Okay? In this test series, total we are giving you 4,000 plus practice questions, in which 40 plus full-length mock tests are there, 30 plus subject-wise tests and concept-wise tests are there. Complete detailed mock analysis would be provided, and you will be given virtual calculator so that you can get the feel of writing the real GATE exam. And all questions are at GATE level because they are created by our experts. Okay. Now you can get our free ebook, scholarship test information, GATE workshop information by subscribing to our BYJU'S Exam Prep channel and by registering through the link given in the description box. Now, here is the first question for you. The Fibonacci series elements are given as input for construction of a heap. It forms what? We know the Fibonacci series are 0, 1, 1, 2, 3, 5, 8, 13, 21, so on. So, if you insert in these elements, so it is going to form what? 0, 1, 1, 2, 3, 5, 8, 13, 21, so on. So, it is going to construct what? Min heap. Because the elements are always in the increasing order, parent will be always less than its child, hence it forms min heap. It is definitely not BST and it is not max heap, and we can't assure of AVL tree because AVL tree should be balanced, height balanced. How many numbers we are inserting, accordingly we can say, right? Next question. Consider a max heap with elements, and however it is not AVL tree. AVL tree must be BST. As it is not BST, it is definitely not AVL tree. Okay. Next question. Consider a max heap with elements 70, 50, so on to 10, so on to 40. After inserting elements 5 and 90, 90 in that order, the level order sequence would be. Do it, guys. Do it quickly. First, given elements, let us form max heap 70, 50, 60, 20, 30, 10, 40. Okay. Now I have to insert 5 and 90. So let me insert 5 first. It is still satisfying the max heap property, no swapping is needed. Let us insert 90, 90. Here max heap property violated. So swap 20 and 90, 50 and 90, 70 and 90. So after 2 elements insertion, level order sequence, if you write 90, 70, 60, 50, 30, 10, 40, 5, 20. So 90, 70, 60, 50, 30, 10, 40, 5, 20. Option C. Right? Got it, everyone? Guys, give some response. Give some response, please. Next question. Consider max heap with elements 90 to 40. After 2 delete operations, the level order sequence would be. Do it. Given max heap is 90, 80, 70, 60, 50 and 40. Now delete root node by swapping with 40. Now 40 should be swapped with 70. So after first deletion, the tree is 70, 70, 80, 40, 60, 50. Now let us do second deletion. How I delete? 70 is swapped with 50, then delete. 50 is then swapped with 80. So, oh, wait. I think it's wrong. I should swap with 80, no, earlier. So 90, 80, 70, 60, 50, 40. Now first swap 90 and 40. delete the last leaf. It still satisfies CBT property. Now 40 is swapped with max of its child, because 40 is smaller than its children. So 80, 40. It is swapped again with max of its children. So 60, 40. So after first deletion, the tree is 80, 60, 70, 40, 50. Now let us do second deletion. So when I do second deletion, '80 is swapped with 50 first. Then delete 80. Now 50 should be swapped with 70. So the elements we are getting are 70, 60, 50, 40. Clear? Next question. The second leaf node in min heap after construction with elements 10, 7, 8, 9, 3, 2, 6, 12, 15, 13 inserted in this order is. Let us construct a min heap. First, insert 90, insert 7. As it is not min heap, swap 7 and 10. So 7 will be parent, 10 will be the child. Then 8, no need of swapping. 9, swap 9 and 10. So 9 would be here, 10 would be here. So 7, 9, 8, 10. Now insert 3, swap 3 and 9 first, then 3 and 7. So after insertion of 3, we have 3, 7, 8, 10 and 9. Now insert 2. 2 is swapped with 8, then with 3. So now 2 became the root. 7, 3, 10, 9 and 8. Now insert 6. Still it is min heap. Insert 12. Still it is min heap. 15, min heap. 13, min heap. So whenever you inserted in this sequence, this is the final binary heap we got. Now what is the second leaf node? You might think 15 is the second leaf node. In this way, level wise you have to calculate. So what is the second leaf node? 8 is the first leaf node, 6 is the second leaf node. So this is the second leaf node. Got it? So you have to be focused. Next, identify correct statement or statements from below. Every full binary tree is a complete binary tree. Suppose I write like this: A, B, C, D, E. It is full binary tree, but not complete binary tree, isn't it? So every full is Naveen Nayak. What happened? What happened, Naveen Nayak? So it is given every full binary tree is a complete binary tree. It is false. And every complete binary tree is not a full binary tree. Acha, previous one. Okay, okay. Yeah. Generally, you might think 15 is the second leaf, but you should count in the level wise. Okay. Yeah. Every CBT is not full. Yeah, it is true. See, CBT can have one node, one child also, but in the full, one child is not allowed. You look at this example. It is complete binary tree, but not full binary tree. So it is true. Every perfect binary tree is not a full binary tree. Every perfect binary tree is not full binary tree. No, perfect must be full binary tree. In the definition itself it is there. So it is false. Every binary heap is a binary search tree. No, not at all. If it is skewed, that too if it is left skewed or right skewed, it is. Again, in the degenerated it is not. But it is telling every binary heap is binary search tree. No. Suppose I am writing 70, 60, 50, 40, 10. It is max heap, but not BST. Because BST means left should be small, right should be greater. Right? So it is not BST. So every binary heap is a BST? No. Hence, what is the correct statement? Only second one. Naveen Nayak, I have explained the difference. Full binary tree should have either 0 or 2 child, that's it. It need not to be filled from top to bottom, left to right. So every full need not to be complete. Similarly, every complete need not to be full. You see the second one example. The second one is complete but not full because B is having one child. And every perfect binary tree must be full. Must be full with the leaves at the same level. Then it is perfect. So every perfect binary tree is not full. That is wrong. And every heap is BST. No. Because in BST left should be small, right should be greater. But in heap all should be small or all children should be greater. Hence it is false. Okay. Next, the number of binary min heaps that can be formed from a set of 7 distinct integers. With 7 integers, so n is equal to 7. So first form complete binary tree with 7 integers. This is complete binary tree with 7 integers, right? Now in these 7, 1 will definitely go for the root. So we have remaining 6. In that 6 we have to choose 3 for the left subtree. Chosen in 6C3 ways. Apply the same rule for left and right subtrees. In the left I have 3 nodes. In that 1 go for the parent. So among the remaining I should choose 1 for its left. And right has only 1, so it can be chosen in one way. Same rule applicable for even the right subtree. So it is 63, 6 into 5 into 4 into 3 factorial divided by 3 into 3, 3 factorial into 3 factorial into 2 into 1 into 2 into 1. So 3 factorial means 6. So this is 5 into 4 into 2 into 2. This is 5 4s are 20, 24s are 80. So in 80 ways we can form min heaps or max heaps, it doesn't matter. Got it? That's all about binary heap. I hope quickly binary heap concept is revised for you with this class. This is my Telegram group link, guys. If you have not joined yet, please do join. CS_by_Satya. You type in the Telegram search bar, you will get it. You may join and discuss with your students, with your friends, and you will get the PDFs, everything. Through this you can communicate with me. Yeah, same formula, Naveen Nayak. That's all, guys. Please don't forget to like the session, share and subscribe to our BEP channel. See you on Monday. From Monday we will have computer networks concepts, very important concepts, and till now I have not discussed those concepts on YouTube. So such new concepts I will be discussing, okay, from Monday. So the next week is dedicated for computer network subject. Naveen Nayak, once computer networks is over, then COA. Okay? Keep liking the session, sharing and subscribing to our BEP channel. See you on Monday. Till then, have a great time. Take care, everyone. Have a happy weekend. Good night. Bye-bye.